Dear students, I welcome all for this session. In our previous sessions, we have discussed what is sorting and what are the different sorting techniques. And we mainly discussed two sorting techniques called bubble sort and selection sort. Today, we are going to discuss another sorting technique called insertion sort. Insertion sort is a simple sorting technique that works similar to the way you sort playing cards in your hands. Here in insertion sort, the array is virtually split into two parts called sorted and unsorted part. The element from unsorted part is picked every time and it is placed at proper position in the sorted part. So this is the main ideology behind which the insertion sort works. Let us look into the theoretical algorithm of insertion sort. The algorithm starts with only one element in the sorted part because we know that a list with only one element will be always a sorted one. So the algorithm starts with only first element in the sorted subpart because an array of one element is itself in the sorted order. Next, in each pass, the first element of the unsorted subpart is removed and is inserted at the appropriate position in the sorted array so that the sorted array remains in a sorted order, and hence in each pass the size of the sorted subpart is increased by 1 and the size of the unsorted subpart is decreased by 1. So what you are going to do is initially you will begin a sorted list with only one element, and that is the first element in the array. And in the next sequence, you are going to pick one element from the unsorted list and you are going to place that element in the sorted part by finding the appropriate position in the sorted part. Hence, in every iteration, the sorted list will be increased by one element and the unsorted list is going to be decreased by one element. And this process is repeated for all the elements in the unsorted list. Okay, so this is just a theoretical description of an insertion sort. Let us now discuss insertion sort with an example. Here I have considered a list with 7 elements and the elements are 8, 5, 9, 3, 16, 4 and 7. Initially, we have to divide this list into two parts. One part is sorted part and the other part is unsorted part. In the first step, I'll consider the first element of this list as a part of sorted list and the remaining n minus 1 elements as a part of unsorted list. Next, we are going to pick one element from the unsorted list, that is the first element in the unsorted list, and we are going to find the appropriate position for this element 5 in the sorted list. So how do you find the position for this element 5 in the sorted list? It is very simple. Remove this element 5 from that position and compare that element 5 with the element in the sorted list. If you find any element which is smaller than that element, the position next to that element will be the position for that current element. Okay. So here 5 is compared with 8. 8 is greater than 5. Okay. But this is the end of the sorted list. There are no elements in the sorted list to further compare. Hence, we are going to move this element 8 to the next position, that is to the position 1, and we are going to write 5 to this memory location. So at the end of the first iteration, 5 will be placed at 0th location and 8 will be placed at the first location. And now the sorted list size is increased by 1 and the unsorted list size is decreased by 1. In every iteration in insertion sort, the size of the sorted list will be increased by 1 and the size of the unsorted list will be decreased by 1. In the next iteration, we are going to choose the first element in the unsorted list, that is 9, and we are going to find the position for this element 9 in the sorted list. To find the position for this element 9, first remove that element 9 from that position, okay, and store it in this and store this element 9 in a temporary memory location. And now compare the element 9 with the last element in the sorted list. So the last element in the sorted list is 8. 8 is smaller than 9. Hence, you cannot do further comparison. You have to stop the comparison process because you have got an element whose value is smaller than the element that you are comparing. Okay, hence you have to stop the comparison operation. And the location for that element 9 is next to this 8. So the next location is 2 itself, that is the position of that element 9 itself. Hence, there is no need for any swapping. The element 9 will be placed at the location 2, and the size of the sorted list is increased by 1 and the size of the unsorted list is decreased by 1. Here in this step, you need not compare the element 9 with the other element in the sorted list, because you know that the sorted list will be always in a sorted order. If this element is smaller, obviously the other elements to the left of this element will be a smaller one. Hence, you need not compare with other elements. Okay. And in the next step, you are going to choose 3 from the unsorted list, and you are going to remove that element 3 from that location, and you will compare with the last element in the sorted list. So 9 is greater than 3. So if the element in the sorted list is greater than the comparing element, you're going to move that element to the next location. So now move this element 9 to the next location. Okay, now 9 goes to the third location, and next compare the element 3 with 8. Here the element 3 is stored in a temporary variable, so the value of this element is not lost. It is there in a temporary location. Now compare 3 with 8. 8 is also greater, hence move this element 8 to the next location. Now the element 9 will overwrite this 9. Okay, element 9 will overwrite this element 9. That means 8 is moved to this location. Now compare 3 with the element 5. Okay, 5 is also greater. Hence move this 5 to this location. 5 comes here. Okay. Now there are no elements in the sorted list to compare. Hence the position for this element 3 is 0. So at the end of the second iteration, at the end of the third iteration, the element 3 will be fixed to the position 0. And the size of the sorted list is increased by 1 and the size of the unsorted list is decreased by 1. Next, you're going to pick 16 from unsorted list, 16 from unsorted list, and you will repeat the same process. You will compare 16 with the last element in the sorted list. So 9 is smaller than 16. Hence, the position for that element 16 is the same position. Hence, 16 is moved to the sorted list, and the unsorted list contains only 2 elements, 4 and 7. In the next iteration, you're going to choose the first element, that is 4 from the unsorted list, and you will compare that element with the last element in the sorted list, 16. 16 is greater than 4, hence you will move 16 to the next location, and now you will compare 4 with 9. 9 is also greater. 9 is moved to this position, that is to the next position where earlier 16 was there. And now 4 is compared with 8. 8 is also greater. Hence 8 is moved to this location. And 4 is compared with 5. 5 is also greater. So 5 is moved to the next location where Earlier, like 8 was there. Now you will compare 4 with 3. So 3 is smaller than 4. Hence, the position for this element 4 will be 1. The location is 1. To this location, you are going to write the element 4. So now at the end of this fifth iteration, the element 4 will be returned to this memory location. And now the unsorted list contains only one element. You are going to compare that element with the last element in the sorted list, that is 16. 16 is greater, hence you will move 16 to the right. And now you will compare 16 with 9. 9 is also greater, move 9 to the right. And again, you will compare 8 with 7. 8 is greater, move 8 to the next location. Okay. Next, compare 7 with 5. 5 is smaller. Hence, you got a location for the element 7. 7 will be placed at the location 3. So, at the end of this iteration, all the elements from the unsorted lists are moved into the sorted list. And this completes the sorting process. And you can see the list is now in a sorted order. Okay, so this is how the insertion sort works. Now let us look into the algorithm for insertion sort. While writing an algorithm, you should remember how we actually performed insertion sort, how we manually performed insertion sort. If you understand the process, understanding an algorithm and writing an algorithm is quite easy. So the input for this algorithm is a one-dimensional array, a list of elements which are unsorted, and the output of this algorithm is a sorted list. So this algorithm is going to produce a sorted list. So let us look into the methodology. Initially, we have assumed the first element, which is stored at the 0th location, as a part of sorted list. And you have to choose the first element from the unsorted list, which is stored at an index value 1. From that location, you are going to pick every element up to n-1, and you are going to find the appropriate position for that element in a sorted list. Ends have started a for loop with the initial value 1, which runs up to n-1. So this for loop is used to represent the element in the unsorted list that you have picked up for placing it in a sorted list. Okay. So initially, the high value is 1. Hence, the first element is stored in a temporary variable. And now you're going to compare this element with the other elements in the sorted list. Now, you are going to compare this temp with other elements in the sorted list. So for that, here I'm using a J pointer variable to point to the elements in the sorted list. Initially, this J pointer is set to I-1. And now I'll compare A of jth element with temp. If A of jth element is greater than temp, what we did, we moved this jth element to its next position, that is to the j plus 1th position. Okay, so we are moving A of jth element to A of j plus 1th position. And now we are going to decrement the j pointer. So this process is repeated until the j value is greater than 0 or an element whose value is less than temp is found. So when any one of these condition becomes false, the while loop is going to terminate. At the end of this while loop, you will be finding the position for this temp, that is j plus 1th position. And to this A of j plus 1th position, you are writing the content of the temp. And this process is repeated for every element in the unsorted list. So at the end of this for loop, you will be having a sorted list. And coming to the performance analysis of insertion sort is very simple and works efficiently for small data sets. And the worst case performance is order of n squared. The best case performance is order of n, and the average case performance is also order of n squared. Coming to the space complexity, insertion sort consumes n memory locations to store n elements, which needs to be sorted. And this completes insertion sort. Thank you.